Howdy, everybody. Hope you're doing well wherever, whenever you are. We are here for day 7 of Advent of Code 2025. Been making progress each day. Again, I don't think today was especially hard. Like you can see, I had enough free time that I'm like, oh, I'm going to try and see if I can't produce like a very optimized solution. And so you can see my numbers right there. Those will fluctuate while I'm streaming. But yeah, I was able to get like P1 down to like 14 micro and P2 down to 16. So I think today I'll show you how I did that, because it didn't feel like a particularly tough day. Like, I think essentially if you thought the problem through, you could kind of track you kind of just track state and just like work your way through the puzzle, and that solves it for both parts. And you just do it slightly differently for each part. So anyway, we'll talk about it more, but that'll be the plan. So, well, what is the problem today? You get out of the trash compactor, you think the cephalopods, and you're now in a lab, but the teleporter that was going to get you out is broken. Magic smoke. I don't have I told you I have a story about this too? My one of my first computer teachers when I was like in high school was having us fix computers, and he was all showing it. He had gotten a new computer part, a new CPU, and he wanted to show us how to do it. And I don't know how this is possible, because it's actually, I think even at that time it's hard to like put it in wrong, but he had put it in wrong, and then he turned it on, and you'd see like a puff of smoke coming in. So anyway, that's all. It was kind of funny because it was his brand new CPU, and he was angry. But okay, anyway, you find a diagram of these tachyon manifolds, and the idea is you're trying to it's you think of it as like beam splitting or something like that, but it's not splitting. We've had problems before where it like hits a mirror like at an angle and goes somewhere. This one, it's always going down. So it starts here and it always goes down, and whenever it encounters one of these, it splits it. And all that means is it's now you need to from one beam you make 2 beams, and from those 2 beams you then keep going down. So those are going to split, and then these are going to cause splits. And so you can see like here's the initial, it hits and it splits. Then those 2 come down here, they hit and they split, and so on and so forth. You get all these little splits. And so what it's asking you is how many times did it split? And one of the ways to think about this is if you look at this solution, in this case, all of them were split except for this one, right? So there's 22 total beam splitters, and only one of them wasn't hit by a beam and didn't cause a split. So that's what kind of led me to my solution, was to just say, oh, well, I can just, if I keep track of where how many beams I have at each location, or like in each column, then I just have to ask myself for each row, how many splitters hit my thing, hit one of my beams, and then I update my state, right? So every time I hit a split, I remove that beam, and then I add 2 new beams on either side. Anyway, that's kind of felt like all it was. So here's my solution to part 1, where I kind of say, okay, we need to parse the grid. My initial solution is just a vec car, right? So I'm just going to create a 2D array, and I want to track where my beams are in the columns, right? So in each of the columns, where are the beams? So I can use a hash set to do that. And I start with where the position of the S is. So my initial, I only have 1 beam, and it's initially like where that S is. Now all I have to do is just go through the grid and say, okay, go through the grid, find all the splitters, and if a beam is in that same column, right? So here's my, maybe I can rename it like that so it's a little bit more readable. But like, if a beam is in my column, in the column of the splitter, then I know I've done a split, and then I just insert my new split, not my new beams, and remove my old one. That's all there is to it. This is technically, I actually think this is, you can, is this? Yeah, I think this is fine. There's an issue when you're optimizing that you have to worry about. Maybe we'll talk about it later. But that's really all there is to part one, right? We're just going to go through each of the rows, and we're going to track our beams. And for each column in the row, we're going to say which ones are splitters and which ones have beams that overlap. By the way, you may be asking why I didn't add this to the filter, and it's just like an ownership thing. Like if I put it in here, this function wants to borrow it, and these functions want to mutably borrow it. And I still haven't figured out a great way to do it, and it's easier just to do it like this. So that's the way I did it. Anyway, so that's part one. So you may be asking yourself, well, how do you speed it up? If you look my initial P1 solution, 90 to 100 milliseconds or whatever. Not super fast, but I mean, still really fast, because again, you're really just iterating through the rows and updating a hash set. So it's hard to like, make it substantially faster, but we can make it faster. And I think the key thing to think about here is two things. One is parsing, and then two is using the hash set itself, right? So from a parsing perspective, if you have this as a string already, well, in Rust, we want to use it as a vec or a byte array. We want to use it as a byte slice. You can actually infer how big each of the columns are, because notice like the grid is like standard layout. So we can figure out how long each like step is, or each stride is, how long each row is, just by looking for the first new line. And then we know how long each row is. And so in each column, so like if I want to index this column right here, or this specific value right here, I can really just say, well, I know it's 2 rows deep plus 1. And then this is 2 rows deep plus 2, right? So if I know how long a row is, I can index directly into the byte array. So you don't have to do any like turning it into a vec or a vec car or even a vec usize or anything like that. You can actually just do that straight up, right? So let's look at how that happens in the P1 fast function. Well, I need to know what my stride is. That's it's the way that I learned it was a stride. You can also just say like the row length. But so I'm going to look for the first position of the new line, and then I know my strides are going to go +1 to that, right? The idea is each stride should get me to this bit right here, this position right here. So if I know this is the end right here, +1 is this one right here. That's going to be my quote unquote stride. So now to figure out how many lines I have in the whole table, I just do the input length div seal stride. And we do this because it's possible there's not a new line at the end. And so you'd get like a, you'd do an integer division. And because it's just like 1 character short, it would actually like give you 1 less line than you expected. So you div seal, meaning if there's any remainder, it's going to go up. It's like partial lines at the end is the way to think about it. Okay, we'll talk about the bit mask in a second. But so now we have our strides and our lines. So the question is like, how do we get like a quote unquote row? And maybe I should call this a row because it might make more sense. it was just like I said, right? So we can we're going to index each line, right? So we're going to have some number. This is like line 0, 1, 2, 3, 4, and so on. Did I do that wrong? 0, 1, 2, 3, 4, and so on. We're just going to say, okay, create a slice from the original input where we start at our stride times our index, right? So this is like the line number that we want to start at. And we go to our stride times the index plus our stride. So that part is going to give us, like, say we're on row 3 or whatever, which is right here. It's going to give us these characters, right? So the stride starts here, and then we go an additional stride, which is technically here, but it's not range inclusive. So that gives us this row right here. So we now have a subslice of the original slice that we can work over, that we can do processing over. And the nice thing about this is it means we don't actually have to modify the array or anything like that, create an array. We just have to say, hey, I want the bytes of our input. We're going to use the bytes of our input, and then we can do that stride. Okay, well, the other speed up is, how do you track where the beams are? Remember, in part 1, we're only interested in tracking like where the beams are in the columns. So it's an on-off switch, right? Is a beam in this column or not? We can actually do that with a bit mask, right? We've talked about these before, but the idea is we'll use the bits of this U128. I think that's how big it had to be to fit all the values. How big was it? Did I get lucky with U128? I think there's like 140 rows. So I may have actually lucked out that it doesn't like split on the edges. So this, I guess, depending on your puzzle input, this may actually not work. But you could imagine if you wanted to, if you wanted to be completely sufficient, you could get like the length of the stride, and then you could just like create a bit mask that's sufficiently large. So a vec of U128s to like solve it. Anyway, so what do? Is we get our beams and we start with the beam at the start position, right? So we're going to set our beams and we're going to OR that with, actually, we could actually just do this one line, right? For this one, like this. Yeah, I think so. So we're going to start with the 1 at the position of the thing. So this left shift is saying like, take that number 1 and move it over to where the start bit is. And now we like I said, we're going to go through each of our lines and we're going to check, is it a splitter, and does our beam hit that splitter for each of the columns in the line? So how do we check that? Well, we just do beams and 1 left shift I does not equal 0, right? So we're basically saying shift a 1 over to the where we're checking the beam, and then we AND that with the actual beam, which will turn everything off except for this one. The idea being, if the beam is there, now we know there's a beam there. So once we know there's a beam there, we can just do this fold on all of those. We do the fold on all of them, I should be clear, right? Because we're trying every column and we're checking, does every beam have a splitter? And for all of them that do, we can now we can create a new beam list, right? So we want to increase our split, but now we remove ourself and then we add our left and right values. So you can see this looks somewhat similar. We're just left shifting instead of removing and inserting right here, right? But we're essentially doing the same thing. And then, so we're going to do that over the whole thing, and that will tell us how many splits we have for that row. And then if we sum up all the splits for all the rows, that will give us the sum for all the things. So that was kind of a long-winded approach of saying, like, my goal of this was like, oh, can we provide like an even faster solution? Is this more readable? Probably not. I mean, if you've got 20 years in the industry and you do a lot of stuff with bit manipulation, maybe it's not that hard. But these actually, I just don't work a lot with bits anymore, and so these actually took a little bit of thinking for me. These ones not so hard. The left shifts and right shifts are pretty easy. But like the question of like, do I want to or left shift not and like this like turn off the value, right? Those are things that you have to think about. This one's not so hard either. I mean, this is pretty common, used a lot. Anyway, if this doesn't make a lot of sense to you, don't worry about it. But I just thought I'd show you. You can see you can go from like 100 microseconds to 15. I think when I wasn't recording, it was like P1 fast is at 13, and then this was at like 15. So it's adding about 2 milliseconds while I'm recording. But again, still not bad. Even with that. So quite a bit of a speed up, right? It's like 4 times. What is that? That's even more than that. 5 times faster. 6 times faster, something like that. I can't math. But that's part 1. Okay, the face of it, part 2 may seem like it's a little bit more complex, but at the end, it's actually not. What they want you to do, and I think I've joked about this before, is like the many worlds interpretation of quantum mechanics, right? Thanks for joining me on this world in the many worlds. Well, what it's saying is these tachyon manifolds, or the tachyon beam that you're sending, the particle that you're sending, when it hits the manifold, it doesn't actually split. It it takes both directions and creates 2 new worlds where one's taken the left and one's taken the right. So what it's asking you is how many times did you how many timelines did you create? That is to say, every time you split, you create a new timeline. So the thing that's a little bit harder about this is you can't just like directly go through and count them like we were doing before, because you may have like split up above and created additional particles that are going down. So like when you hit the next splitter, the question is like how many particles are going to hit this specific splitter? And the answer may actually be not 1 anymore. It may be 30, because there's been 30 different splits that have caused a beam to potentially go down that path. And so it shows you here. Here's an example. Here's one timeline of the tachyon that always went left, right? And then here's one where it went left and then right and then left and then right and then left. So it was alternating, right? Here's another timeline. So they give you a few timelines, and this is all to say there's a bunch of timelines to think about. Now, I suspect you could answer this one with something along the lines of like dynamic programming. Like, because the question you just have to ask yourself is how many times does this beam get hit? And then that will tell you how many you basically double that number is the way to think about it, right? If that beam was hit 30 times, well, you now know it's going to create 60 timelines in total. And so like, how do you answer that question? Well, you need to know how many times was this beam split, because this beam is associated with this one, right? So I could see maybe doing a DP type solution where you do like a DFS down, and then you work back up, and slowly you're like solving. I think that works. There's actually an easier way though, right? If instead of counting where the beams are in each column, you can actually just count how many beams are in each column. And so as you're moving down, right now there's only 1 beam in this column. When you hit this one, there's now you know there's going to be a beam here and a beam here, right? And then when you hit this column, you know now there's going to be like 2 beams here, 3 beams here, and 2 beams here, right? So maybe I'm not explaining this very well, but the idea is there's now 2 beams. We created like 1 new timeline, but when we hit this, we create a timeline here, here, and then for this one, we create a timeline here and here. So there's still 1 timeline here and 1 timeline here, But they were created from the timeline up here above, right? So there's now 1, 2, 3, sorry, 2, 4, 6 timelines in total, right? Is maybe the way to think about it. And if you're just keeping track of in each column how many timelines are there, and you work your way down, eventually you get to the solution. And so that's the solution I came up with for part 2. So here's my part 2 solution. You can see it's my initial part 2. It looks very similar to part 1. We're going to go through the row, all the rows, and for each of the rows, we're going to say, where are the beams? And we're going to ask, do the beams overlap? And if they do, we're going to update the beams in each of those columns. Did I say rows again? It's actually columns. Update beams in columns. So we want to start by inserting the beam at S, and then we know there's one beam there. There's like one timeline. We're starting at one timeline, right? So we find S and we start at one timeline. When that first one hits the splitter, we're going to remove that timeline, right? Because now that timeline is now split over 2, and we're going to we're going to increment the counts of its neighbors, right? The reason we do it in a hash map, at least the reason I did it, is because as you're adding or removing beams, you obviously, like we had mentioned right here, this beam, there's going to be multiple beams from this one, because this one created a timeline where it went left. This one created a timeline where it went right. So there's actually like 2 timelines going down this path, if that makes sense. So this is all you do. You just say, hey, for each of the splitters, if I can remove a beam, this is kind of a hacky way of, I thought it was a clever way actually, but we're saying we're going to try and remove the beam from the hash map. And if I successfully do that, I now know how many were there, and now I can update the neighbors of that beam using my entry. I think we've done this before, right? Get the entry or insert it with a 0, dereference it so we can add the count to it. And that has a way of like updating the map inline. And then once we're down at the bottom, once we've gone through all the rows, we just count up all the timelines in each column. So we get the values and we sum them up, and that gives you your answer. This actually runs faster than part 1, and it's not totally clear to me why. I think it has to do with the way hash sets work and the contains, insert, remove. I wonder if I could do a remove in here as well, and that might speed it up a little bit. But you can see I'm doing a contain, insert, remove. This one, I only have to do a remove and then entry or updates. So I'm updating the entries here, whereas these ones, I'm like always adding new ones. I don't know. It was a little odd that it went fast. Well, how do we do this one faster? Think about how we solved P1 fast. The only thing that's really changed is, okay, how do we track the number of timelines, right? How do we track the timelines in here in this loop? And again, if you think about what we're doing here with the hash map, we can actually just use an array, right? Instead of having a hash map, what if we just had an array that contained all of the values, all of the timelines in the columns? And then we can solve from there. So that's what I do. We again, we get our strides and lines. We have our timeline values for each column. And I think 142, it's a magic number. I think it's the actual length of the strides that I put in there. But this allows me to like make it without having to like allocate it on the heap or whatever, right? But then we just say, okay, set where the start position is in the timeline to 1. And now this is going to look very much like part 1. The only difference being is when we found a timeline, the way we say we found a beam that hits some timelines is obviously it needs to be a beam splitter. But then the timeline, the value in the array can't be 0. And so if that's not the case, then we want to update the timelines. And how do we do that? We just initially we get the count, and then we say set the next beam. Oh, we do have to do next beams here. This was an interesting problem I ran into when I was trying to do the fast solution. There might be a way to get around this, but I kind of gave up trying to do it. We basically make a copy of this array, and we're going to update it each time. And like the problem I ran into is like there, because it's an array and we're not like iterating over values or using a hash set to track it, it's possible for us to update a neighbor value, and then in the next iteration the neighbor value is used, and so you get an incorrect answer. So we actually are going to we're going to update like a next beam. This is a little bit like we've solved Conway's Games of Life before. It's easier to just like treat the array, create like a new array that you're going to update, and then swap them. And the compiler is smart enough to say, oh, I'm just going to keep two of these and kind of work between the two, right? Anyway, what do? We get the count from our current position, our current column, and then we set that one to 0 because we now know all of those timelines are now going into its neighbors, right? So we increment the neighbor on this side and the increment neighbor on the other side. And then once we've gone through all of them, we update our new timeline. Then all we have to do is go through all the timelines at the end and sum them up. So, I mean, is this DP? Kind of. I mean, technically, you could argue I'm doing DP, I've just unwound the loop or whatever. So, but it feels a lot faster than like if I had tried to DP a functional like EFS call or something like that. That was the thing, and I don't know. We'll go look at the problems. But my initial thinking was, oh, maybe is this a DP problem? Maybe we try and solve it with DP. And like the more I thought about it, it's like, oh, I actually don't need to solve this with DP. I can literally just track how many timelines are in each column. And so that made it easier for me. So anyway, there's the code. Again, I don't think this day was particularly hard. I don't think it would fit in the easy category just because of like the complexity of this stuff. So maybe it is in a medium, but it's not one of those days. I mean, I've had days in Advent to Code on like day 5, 6, 7 where it's like, and maybe that will still come. So can't hear this, but I'm gonna knock on wood. Maybe I'm getting better at this. That's very debatable. But these days didn't seem too hard, and I was able to. This one I actually solved in the evening. It was late Saturday night, and I was like, oh, I should just try and solve it. And so I solved the P1 and P2 quick enough that I was like, oh, this isn't going to be an exciting like showcase of code unless I like do something extra. So today I did the the fast versions, and then that's where we got. So okay, so where are we at with all of this? Yeah, I don't think it was a crazy tough day, but here we go. Day 6, 7, 8, AOC. Yeah, I am a little worried that some day is going to go a little too hard. I think the grid is pretty big. When I accidentally destroy the wave function because I want to look at the tachyon. There you go. Quantum mechanics jokes. They're about as funny as my dad jokes. Wow, that's crazy you were able to do this with Excel. Cool. Okay, looks like we got a lot of visualizations. Kind of fun. Yeah, there are some interesting ways that you might be able to solve this. Like if you look at this visualization, like you could imagine you just have to ask yourself, like at any point, could the beam have gotten to me? And if the answer is no, then you're not there. I mean, essentially that's what I did, but from the top-down approach. It does feel like what's going on is a little weird here. That's for sure. I mean, okay, yeah, I suspected there'd be people who solved it DP. We'll look at some solutions. I actually don't think it's like too crazy. Yeah, so this is exactly what I did, right? Is you can kind of just keep track of all these values as you're going through the road. Same thing with these parts. I mean, the difference between this is you need to have like counts, right? You want to have counts of how many times. I have no idea what I'm doing. I I suspect you do. Don't sell yourself short. I mean, I know I like to joke about like how stupid I am, but you know, I think we're all solving we're all solving puzzles. But yeah, like I don't think I would put, and maybe I would be interested to see what you all say. But I don't think I would put my solution into a specific category of DFS or BFS because it's literally just a linear scan where you're tracking state for both of them. Uh, it is a large number, so if you were using U32s or whatever, that happened. Okay. Okay, let's look at some solutions. We looked at some memes. I already went down so we could see. Follow Jonathan. Get your start position. I mean, this is a very generic solution, so yeah, that works. So you start at the start position. You've seen it before, you skip. Otherwise, you add it to your scene list. If you go out of bounds, you leave. Excuse me. If you get one of those, you add them to your scene list and increment part 1. This is it simple enough that it always goes to the next row? I'm curious how fast this solves. I kind of want to do it. I could type. And that's pretty fast, 18 millisecond. Uh oh, but we're in milliseconds, right? Not microseconds. I don't think I have the special pi that makes it faster. I don't know how you get better than like a table scan though. Like I think the DP solution, even if you're caching results, it feels like it's faster. Can I look at the puzzle really quick? Do I not have the right solution? Was my vec not big enough? Like, I presume it would cause splits. 1, 5, 6. So if it's interesting that my P2 fast solve. Um, I think there's actually a logical error here that won't work if the splits happen too early, but just happen to be working for this size. One U128 is not big enough. So this may be an actual logical error. Try and fix it right now since I kind of haven't done much. We could just do an array. This is not going to be as fast. Try it though. Dreams. Yeah, that slows it down a lot. Oh, I mean, that's even slower than my original solution. Um, let's see. What is another way? I don't. How am I getting these right? E1 fast. E1 fast. I would presume this would produce incorrect result. Let's see. I really don't want to do the I don't think there is. I don't want to use arbitrary size. Okay. We'll have to like I think the way you do this is you create like a bit mask. So we that. This. That. And then we do. We want to do. We just want to ask questions. So we do fn set. It would be self. It would be the right here. But it would be self one. We go I plus. In this case, we're just going to I. But it would be index. This. I did that. Bug. Are those right? Do I have to do this? This? Okay, so let's try this. Try. New set. And this is where I'm gonna this. Okay. That should work for the puzzle now. I don't, and it didn't add too much time, right? I'm still getting the right solution, right? Yeah. So what do I do? It didn't fit in a U128, so I did some extra work to make sure it did. Basically, we have two U28s, and we just have to ask ourselves, am I trying to set, unset, or check a value that's greater than 128? If I do, then use the second, right? Otherwise, use the first. There you go. Okay. That makes me feel a little bit better. Did everyone do the dynamic programming solution? It's hard to compare because these are Python, but I suspect the dynamic programming is not the best. I don't think it is. I mean, I you can definitely solve it that way. I'm solving the right puzzle, right? Day 7. We're on day 7 solution. Yeah, okay, there you go. This is a great this is where I came to my solution. And so I suspect it's similar. Yep, look for this and then just go through all the lines. Oh, they keep track of their points. A hash set? By what? Oh, it's a hash set per line, so you know where they are in the line. It's probably not necessary, but I see what it is. So you now have a list of hash sets, and each hash set says in the row, here's where they are. Yeah, and exactly in part 2, like in part 1, if you're splitting, you just add one, and then for part 2, you just need to track. Hey, do I update my timelines on the other sides and remove? If you do have to remove them too. Anyway, very similar. This is great. This sorry, there's so many. I have so many comments open. 30D. I don't think it's that fast. I don't think what I'm doing is technically deep. I mean, dynamic programming is a very broad category, right? It's like, can you break a problem into smaller sub problems? And so if you generalize any solution up, you can say, oh, the whole thing is DP. But here's why this one is like more traditional DP. If you look, like what it's doing when it's trying to solve a line, it's figuring out the solutions based on what are the next solves, right? Does that make sense? And that's where it's very traditional DP. That's what we saw from the previous Python solution from Jonathan Paulson. Is like, the idea is like, you to solve this one, I need to solve this one, and to solve this one, I need to solve this one, and you do that back all the way down, and then that bubbles up, and you're memoing so that if you ever get back to those states, then you know you've done that. But because there's no decision making, if that makes sense, you're not making a decision. Like that's where DP is especially helpful, is like when you need to make a decision. And so you're saying, well, should I put it in slot A or slot B? And when you're doing that, oh, maybe that's why people felt like you're in two timelines. So did you go left or right? And then you say to yourself, well, what is the solution if I went left? What is the solution if I went right? And then you DP. So I guess I can see, and I think I said this earlier, I suspect people would think you could do it with DP, but I don't actually think you. But that does, I now kind of understand more, is like the idea is if you presume each side is its own like DP problem and then you like work your way down, I can see how you get to that point. So this does make sense. Okay. But again, you don't have to, I don't think you have to do that. Okay, here's a uh parsing 18, same implementation, just counting different things. Simple BFS on a grid. I don't, I mean, I'm technically not a BFS either. I'm just row iter stepping. Okay, they are parsing tiles. Yeah, I mean, I don't really parse at all. You just give me the bytes, I'll solve it. You always step by two? Is that something do I need to look at the input again? Does it just happen to be it it does look like it's alternate. So that is a potential speed up. You could alternate. That's interesting. That's a cool idea. And so that's one of those things where you're like, oh, I should look to the thing and ignore every other two. I wonder if that actually helps me. Let's see. In my P1, can't really do it in this one. Yeah, it's probably the. It's marginal. One could argue it is slightly faster. I mean, that is some time. Not nothing. I mean, that does speed it up. So very cool. That's a cool optimization that I didn't see. So that's very cool. But again, sometimes it helps to look at the grid, and it actually does help me solve faster, right? I'm getting down into like I'm well easily into the teens now. Um, yeah, so okay, keeping track of a pending and a next is kind of like what I was doing, right? You could alternate the two, right? And I think that's what they're doing here. Pending, next, next, pending. Just like swap them. Yeah, okay. Very good. How are they getting these times though? I guess you have to like read the thing. I mean, you can definitely get it really fast. They may just have a better. The hash maps and hash sets are relatively slow. Yeah, there you go. I hard coded these. The thing is like you can allocate it, but like it's not on the stack, right? It's on the heap. I think I still have heap. I probably still have a bunch of heap allocations because even though I start with this thing, I like make a copy of it and then switch it. Although this this is possibly heap stack allocated. All of these are like heaps though. I don't worry myself too much with this, right? It might be fun to try and over optimize them. You know, look at perf and see where all the time is spent and see if you can optimize it even further. This one's probably pretty hard because you're already doing bytes. Like the way that the tricks that you'd have to do if you're trying to optimize this. Just to be clear too, like Rust already does a pretty good job of optimizing. So like when I do this for in input, iter, enumerate, filter, those things, you might say like, oh, that's adding time. This all gets like turned into a for loop with breaks and you know, jumps and stuff like that. That like if you had written it in a traditional syntax without like the functional aspect of it, would look exactly the same. So at the end, they call it like zero cost abstraction, is like you're doing these, you're saying, I want to do this stuff. And like it translates into machine code that's very dense with just do this stuff. Which is what I think is really cool, right? Like I've done other languages before where like you're like, oh, I want to use some cool function that they have, but then it's like 50 times as slow as if you had like written the manual of it. So what would you have to do? Where would you even look for improvements? If you could update these timelines, I mean, you'd have to see how it does these, like make a copy of the beam and then update the new one and then swap the two values. I don't suspect that's a lot, but you may be able to have like a two pointer thing, like we looked in the other solution that might speed up. You do so little searching. You're only searching for the first new line, and then you're searching for the S. That I suspect. Well, you could potentially do these two in the same lookup. Uh, like you could do a single SIMD. I don't think you actually can. And you'd have to test, is it faster to do a for loop and check for this and this? But you could potentially get these in one scan, so that might speed it up. I'd have to think about how you do that, but you get your position scan, see the speed. Again, we're talking about like speed here, and even my P1 like quote unquote naive solution solves in 100 microseconds. So we're not talking crazy stuff here. Okay, let's refresh and some of the solutions. LRU cache on the GPU. Oh, they're actually like setting values in the thing and seeing if it would like hit or whatever. Okay, that's cool. You're like actually up there. It looks like they're actually updating the grid with like the beams. Common list versus part one. Oh, bummer. That's still good. So what is the change here? This one's a little hard. I think because of the way the common list is structured, you probably have to do a DP style solution with some caching. But I mean, you can still do. Let's see. Python. Yep, there you go. That's exactly what I got. Is it my laziness that just helped out? I'm like, I don't even think I have to do DP on this. Like I was, yeah, I was like, oh, if I have to, I'll do it. But excuse me. Yep, pass. Keep track of the list and solve it. Yep, exactly. Yeah, I think that was the trick is like you again, there's like multiple ways to solve puzzles. There's like many of them you can like brute force. Even some of them are like harder to brute force, but you parallelize. Some people will say, "Oh, I use Dijkstra's," and others will say, "Oh, I use BFS." Those are like one and two of the similar things, right? I don't think you need to do much with this one. Find all paths, hash. Yep. Okay. If you're using a hash map on part two, I think you like figured out the quote unquote trick. So that's cool. Okay. I think that's probably it, right? I mean, memo for part two. See, I imagine in C it would be easier to do it the other way. You actually don't have to like do the memo. Like if I was using a language like C, I think it would have immediately led me to my quote unquote fast solution. Okay, but yeah, you can definitely like this is a cool way to memo because you're like really just memoing the size and rows. This solution is actually pretty close. Then the fact that you're calling it recursively is interesting because if you think about what you're doing here, your memo is actually like the memo of the row and column that you're on. Well, if you're keeping track of the memo of the row and column you're on, you might be able to largely say, oh, well, why don't I just go down all the rows and keep track of the column values? And boom, you're done. This would be a very different problem, by the way. We've had days where like the splitter like sent it different directions, and then you had to track all the different directions. That would be a very much DP oriented problem, at least in my mind. Someone smarter would figure out a better way to do it. But I think I happen to get a good way to do it this day, so I feel pretty good about it. Anyway, tell me how you did. I'd love to see your solutions. Send them my way. I love reading the Reddit threads. So at me on the Reddits and I'll look at your solution or add it to the gist. I'll check it out as well. It's fun to look at those solutions. I feel like just when I look at a problem, it helps me grow, helps me get better. So there you go. Thanks, everybody. And we'll talk to you next time. Bye.